Hi and welcome to this video. This video is a summary of a popular Coursera course on generative AI with large language models. If you want to get more information, the course is the page you should be going to. This is the course page. And in this video, we are going to go through some of the key points which have been covered into the course. LLMs, generative AI are fast moving areas. So many topics are still under active research. Nevertheless, the course introduces to a lot of jargons and keywords related to the subject. Let's get started. Generative AI is an evolution of machine learning. It's a branch of machine learning which aims at generating responses. An example could be generating image from a text, as you can see in this. You give an image, you give a text and you get a generated image. Ideally, it should be as close to the requested text as possible. Another example of generative AI is to have different variations of a face generated. So when you unlock a device like a phone with your face can have different look and feel at different points of time, with or without glasses, with long hair or short hair, with or without makeup, etc. So a generative AI which is capable to generate different variations of the face is better suited to identify the actual face to unlock your device. Now, LLMs are the neural networks which are trained over massive texts. LLMs stand for large language models. When working with language or text, generative AI has multiple use cases. For example, giving answers to the questions or generating source code based on the code comments. Well, this is a new feature which is getting adopted in a lot of frameworks, including Apache Spark. In LLMs, we will see more of the use cases, but what happens in LLM is essentially they are a machine learning model. They are built of neural networks. The input which we provide to the LLM is called prompt. The output which is generated from the LLM is called completion. And the size of the prompt, the size of the input is called the context, which is the context window, can typically allow a few thousand words. In this case, we are asking a question to the LLM and we are getting a response, an answer in the response or the completion. Some of the use cases of LLMs are essay writing, where you give a topic and you expect some essay on that topic. Summarization, where you give a larger body of text and you expect a summarized version of the key points. Translation from one language to the other. Retrieving information or identifying the entities in a text. For example, you may have a story and you would like to know who is the protagonist or the antagonist, or which location is this story set up. And another use cases of LLMs are in interacting with the external integrations, like external data sources, or invoking any external APIs and action. We will take a look at this part towards the end of our video. What happens during prompt is you can provide some examples into the prompt or the input when you are asking for the response from the LLM model. Based on how many inputs do you provide into the prompts, it can be one-shot inference or a few-shot inference. In fact, zero-shot inference as well if you do not provide any input. In this case, if you have a statement and you would like to classify it to be positive, negative, or neutral, and you are not providing any example, this is a zero-shot inference. If you provide one example, like classify this review, there is a review and there is a sentiment. This is the example you provide as an input. And then you ask the model to classify another review based on this example. Then this is an example of one shot inference because you are giving one example. Similarly, there can be more than one examples given, and that is called few shot inference. Usually, it could be 5 or 6. Some studies have shown that after 4 or 5 shot inference, the model does not give any better result. But these are how the different short inferences are. And this is also called as in context learning, because this is the context window. And based on the examples of the context, LLM gets some hint, it gets some clue on how to go ahead and respond to the final question which has been asked. Well, LLMs, there are a lot of them. And the circles over here are based on the number of parameters an LLM is trained on. We will talk a little bit more about parameters as we go ahead. But usually, if an LLM is having a lot of parameters, it is expected that LLM will be able to capture complex patterns in the text, and it should be able to give you good results over different tasks or different use cases. That may not always be true, and we will see that in a while. But you get a sense like Bloom and GPT have lots of parameters, whereas Palm and Lalama have far less number of parameters as compared to GPT and Bloom. Now, what's happening? What was happening before LLM? So neural networks have been there for a long while, and in order to deal with variable number of inputs, there is a RNN or recurrent neural network. As the name says, recurrent neural networks are recurring or repeating neural networks to handle variable length of inputs. And with long-term memory and short-term memory, RNNs can predict the next word. So one of the major use cases of LLMs is to predict what is going to be the next word or the next token. And let's say we have a sentence called tastes, and there is some part of the sentence before which we don't know, and we would like to predict the next token. In order to predict what will come after this word, it's the more idea we have or the more information we have about the preceding words, the better will be our prediction. Think for an example. If you have to guess the last word of a sentence, assuming you know all the words of the sentence till the last word, and you have to guess that last word, your prediction is going to be more accurate than if you know just one word and then try to predict the next word. Now, think even further. If you are able to read a whole book, and then if you have to guess what comes at the last page, what is the last word at the last page, if you have read the full book and you remember the whole context, it will be much more easier to predict the last word. And in that case, the output is most likely to be the right one. So the whole point is, the more you know what has been coming till far, the words which you have seen so far, that will strongly influence what's going to be the next word. So just by looking at one word, trying to predict the next word, it's going to be most likely it's going to be incorrect. So in order to increase the accuracy in your prediction, you try to go and see more words before you predict the next word. Well, in order to do that, it's possible, but with RNN, the size of the recurrent neural networks grows the more back you go in the context. So the longer context you choose to predict the next word for better accuracy, the size of the RNN is going to grow in accordingly. And even after these 3 words, let's say after these three words, you make a guess like the next word is great. This is also not guaranteed to be correct, because what if the actual sentence was something like this? The milk is bad. My tea tastes, of course, something not great. So even with larger RNN or larger recurrent neural networks, prediction of the next token is not guaranteed to be always right. There are a lot of chances where it can go wrong. So in order to overcome these shortcomings of recurrent neural networks, a transformer architecture was proposed a few years ago by researchers from Google Brain, Google Research, University of Toronto, and so on. We will take a look at this transformer architecture. At a first sight, it looks a little messy. It seems to have a lot of arrows and lots of components, but we will try to decompose this and deconstruct it in a way that we are able to understand what are the different components to it. For now, all we need to know is there are a couple of neural networks involved in the attention layer, this multi-head attention and feed forward. This part is the encoder and this part is the decoder. There is a positional encoding involved. There is some information transfer between encoder and decoder called as encoder decoder attention. We will take a look at all these things in a while. So this is how the transformer architecture looks. This is where we provide the inputs, and this is where we feed the outputs as it is generated. And the output result is the probability of different tokens which can come next. We will see that a little bit more in coming in a while. So transformer architecture is composed of two components. One is the encoder and a decoder. Encoder is where you pass the inputs. Decoder also takes inputs, and the final output comes after the softmax, which comes after the after the fully connected neural network. The purpose of encoder is to generate context, find the context of between the words in the input sentence, and the purpose of decoder is to generate the next output word. We will take a look at example as well. Let's do that now. Let's say, in order to go for examples, first understand embeddings. Computers don't actually work with the words or the alphabets as humans do. Rather, computers translate them into numbers, or basically an array of numbers, or a bunch of numbers, which are the representation of different words. So in this case, the teacher taught if this is a part of the sentence, every word will have a token, which is a numeric representation of that word. Based on the language, if you talk about English, there could be thousands or hundreds of thousands of the words. So every word will have some unique mapping, some number. That is called the token ID. The tokens are fed as input to the encoder and also to the decoder. Let's focus on encoder for now. And then for each token, embeddings are generated. So for each token, embedding is an array of numbers or a vector of numbers. And if two words have similar context, or if they are close in meaning and context, their embeddings will be near to each other. And the similarity of embeddings can be guessed or estimated using the dot product of the vectors as well. So for each token, there could be a collection of hundreds or a few hundreds, like 512 different numbers, which explain what is the embedding for that word or that token. Now, if you have a sentence, which word comes at which position, or which token and word can be used a bit interchangeably. However, they may not be the same all the time, but for understanding, it makes sense to have them used analogously. So which token or which word comes at which position is quite important to have the better understanding of the whole sentence. And that is why Once the token embeddings are calculated, they are added with the positional embeddings. So positional embedding plus token embedding is what goes as input to the encoder. Encoder has two neural networks. One is the self-attention, and then there is a feed forward, which is a fully connected neural network. What happens in self-attention is it tries to find which two words are the most similar in a given context. For example, if we have a sentence like the teacher taught the student with the book, after the self attention, teacher will be most likely be connected to book, and so on, student as well. Teacher and student will have a greater similarity with the book. Now this is something the model learns during training, like which pairs of words have higher similarity than the others. With the help of positional encoding and with the help of self attention, the encoder is now able to have greater understanding of the context of the sentence. And this self attention need not to be having just one head. There could be multiple heads or multiple cells of the neural networks involved at each layer when it performs the self attention. The output of the self-attention is then passed to the feed-forward network in the encoder and decoder as well. So encoder and decoder, you see, they have very, very similar architecture. Both have self-attention, both have feed-forward network. However, their purposes are a little bit different, but their architectures have a lot in common. So after the feed-forward network, let's go one step back. So so we have word embeddings, then we have positional embeddings once they are combined, and then we have self-attention. After self-attention, the output goes to the feed-forward network of the encoder. And then this encoder shares this result with the decoder as well. So in the decoder, it knows all the context of the input sentence as seen by the encoder. And the decoder then generates a token, which in not one token, but essentially a bunch of tokens with different probabilities. So after the softmax output, you have a token along with what is the probability of the token it should come as the output. So think of it like this way. Think of only for the decoder. If the decoder has been trained on hundreds of thousands of different text documents, and in most of the documents, it has seen that the sentence starts with the, then the probability of the first output token from the decoder will be high for the. And let's say the decoder has seen that the second best probability is a. That's the start of the sentence. So the probability for a is going to be second in the output. Now, but here the decoder is not working in isolation. As we have seen, decoder knows what the output of encoder is. So there is one encoder decoder attention where some information is exchanged between encoder and decoder. So decoder will not decide on its own arbitrarily or randomly. Rather, decoder will consider what is the output of the encoder, and that will influence what the probability of different tokens look like in the output of the decoder. Essentially, if you choose the token with the highest probability, most likely that's going to be the first output token based on your input. Now, if we talk about sequence to sequence task, let's talk about translation from one language to the other. This is our input text. The input text is tokenized. It is passed to the encoder after adding with the positional embeddings. And the first neural network in the encoder is the self-attention, which will try to find which two words in the input have the share similarity in the context. That goes to the feed forward network or the fully connected neural network. This attention is then transferred to the decoder. Decoder, the initial input to the decoder is usually uh, end of sequence or a start of sequence. So now we are going to generate output. The first input to the decoder will be, let's say, start of sequence. It can be end of sequence also. Sometimes end of sequence looks confusing because it should be the end, but a lot of times decoders start with end of sequence as well. Now the decoder will take all the context information from the encoder, and it will predict which token has the highest probability to be in the output. Now this is the first token. This will be translated into text. This token has the highest probability, and this is the first output token. This is the output which the decoder has generated so far. This output will be fed to the decoder, and with the attention or the context from the encoder, it will generate the next output. So the process of creating the output will continue by the decoder unless end of sentence or end of sequence is reached by the decoder. So decoder has to keep track of the context from the encoder plus what words or what tokens have been generated so far, so that these two things influence which tokens will be generated the next. And this is all about generating text, which can be used for essay writing, or it can be used for question answer, it can be used for text translation as well. That is the essence of this transformer architecture. And this is how you can convert the tokens back to the text. So now I think now the transformer architecture should make a little bit more sense. Now you understand the embeddings, the positional encoding, the self-attention, the feed-forward network in the encoder, and in the decoder we have this attention. A part of it comes from the encoder, and then there is a masked multi-head attention. So what we saw before is decoder needs to know what text it has generated so far. That will also influence what text should come next. And in order to take into consideration the texts and the relationships between, or the similarities between the texts generated so far, we need an additional self attention called as masked self multi-head attention in the decoder. This multi-head attention and masked multi-head attention have a lot in similar. The only difference is the multi-head attention takes into account the similarity between all the words, whereas masked multi-head attention considers the similarity between only the words which have been generated so far. In the course, they also talk about there are different configurations you can use when you are working with LLMs. So these are called inference parameters. Max new tokens means how many new words or new tokens you would like to generate from the decoder. Sample top K and sample top P are used to provide some liberty or some creativity to the LLM. So if you always choose the token which has the maximum probability, you will always end up having the same sentence. Whereas if you say top P, now there you can say like, okay, I want to randomly choose, not randomly, but I want to enable choosing from top 3 probability, the words which have the top 3 probabilities. I wanted to allow choosing from all of them. So these parameters are used to add some creativity to the generation of the text. Now, the transformer architecture introduces two components, encoder and decoder. Different models can have different transformer architectures. There could be models which are encoder only models. There could be models which are decoder only models. And then there are models which make use of both encoder and decoder. The encoder only models are also called as auto encoding models. And the way they are uh, trained is while training, or basically while testing the model, we mask a token or a word and let the model predict what the masked word is going to contain. It uses bidirectional context in order to understand or guess what the masked word is. So the objective is to reconstruct the text, and this auto-encoding models are not, they are not used much, but their use cases involve sentiment analysis or the word classification. Then we have a decoder only architecture, which is also called autoregressive models. Over there, we try to predict what is going to be the next word. So it tries to generate the next token based on the tokens which have already been generated. It has unidirectional context. And then this is used for text generation. GPT an example is an example of autoregressive or decoder only model. And then sequence to sequence models make use of both encoder and decoder. And here, the objective is to reconstruct a, a range of text or a span of text. So what we do is during testing, we mask a span of more than one token, and that's what. And in the decoder, we try to reconstruct this span, like what words would fit in that span. This sequence to sequence models are best suited for translation and text summarization as well as question answering. T5 and BART are examples of sequence to sequence models. In Whenever we are working with a generative AI project, the there are four major steps to follow. The first is you have to define what use cases you are going to solve. Are you going to work on a specific use case like entity identification or question answering, or you would like to have generic use cases like text translation, summarization, question answer, and so on? Based on that, see if there already is an existing model which serves your use case. If it exists, it's the best. Else, you will have to train your own model. Training your own model is a lot of effort. It takes time. It takes compute. It is expensive. It needs a lot of data. So if you can find an existing model, that should be your first choice. Even if the existing model does not perform that well, you have the option to do prompt engineering, like in context learning, like one shot or one shot or few shot inference, or you can do further fine tuning of the model using some of the techniques we will see soon. Also, a lot of times models are not honest in their response, or they are not helpful, or they are harmful in their response. So we have to align the model with the human uh, feedback, or with after the inspection by the humans. That is also one of the steps to follow. After prompt engineering or fine tuning or align with human feedback, we have to evaluate whether the changes which we have made to the model are taking the model towards the right direction or not. So this adaptation and alignment of the model is like a cycle. It has to repeat till you reach an acceptable level of performance. Finally, once the model is ready to be deployed, we have to optimize the model so that we can get inference really quickly, and we have a smaller footprint in deployment. LLMs on their own don't are not the silver bullet. They have their strengths, they have their limitations as well. So LLMs are also prone to be incorrect on many occasions. So we have to augment our model with LLM powered applications so that we enrich the power of the LLM, or we complement the power of the LLM with external applications or external integrations as well. We will see that as well. So let's go next. Let's see how difficult or how expensive it is to train an LLM. Let's say We have an LLM of 1 billion parameters. The parameters are the weights of the neural networks. And if the parameters are stored as floating point, where every parameter takes 4 bytes, for 1 billion parameters, we will need 4 gigabytes of memory to store just the parameters. But in neural networks, as it turns out to be, that parameters are not the only main concern. The other variables which are used are the optimizer states, gradients, activations, and temp memory. So overall, for each parameter, we need 24 bytes of memory, which means when it comes to train hundreds of billions of parameters, it's not practical to use a single machine. So there are a few techniques to improve or to reduce the memory requirement. One such technique is quantization, where instead of using 32 bits for the floating point numbers, we try to use a smaller bits. It could be integers or 8 bits, or it could be FP16, which is the floating point 16 bit, or it could be B float, which stands for brain float, as proposed by Google Brain. So there are ways to lower the precision of the floating point so as to save some space. So as an example, FP32 uses 32 bits. The 1 bit is for the sign, positive or negative, 8 bits for exponent, and 23 bits to represent the fraction part. It is able to uh, have a minimum value from this to a maximum of here. By reducing the precision a bit, what if we use 1 bit for sign, continue using 8 bits for the exponent, but for the fraction, instead of 23 bits, if we use 7 bits, that's what which is used in the brain float, we will have a truncated floating point, which will still have a reasonable precision, but half the space requirement. So it will have half memory requirement. And these quantization techniques are very popular in order to optimize the model for deployment or optimize the model for training. This is the summary of different quantization techniques when you move away from 32 bits float to 16-bit float. If you move to 8-bit integer, the possible range of numbers you can represent is very, very limited, but your memory footprint will be much more lower. So as the model size increases, quantization is one thing, but still it will not be enough to make the memory requirement to half. For example, for a 500 billion parameter model, you will need 40,000 gigabytes, which is close to 40 terabytes of RAM if you use 32-bit precision. Even if you use 16-bit, your requirement will still be terabytes of RAM. Now, a single GPU, most of the GPUs don't support terabytes of RAM. They support a few tens of RAM, and which means it's not possible to train your model on a single GPU, even after quantization. Well, quantization can reduce the footprint substantially, but still to train bigger models, it's not possible on a single GPU. So we need to split our model training across multiple GPUs. There are two interesting techniques for that. One is the distributed data parallel approach, where you have a whole data set where you would like to train your model. When working with large language models, you have a lot of parameters to train, which cannot fit on a single GPU. That's one problem. The other issue is you also have to train on massive data, petabytes of data. And in distributed data parallel technique, what's happening is you train the whole of the LLM across different GPUs. And instead of training on the full data, you train on a part of the data or a subset of the data. And then using forward and backward pass of the neural networks, you update the model with the gradients. This approach will reduce the amount of data which is on which the neural network is trained on each GPU, but the whole of the LLM will reside on each GPU. So it can solve, it can lead to faster training if the LLMs can fit on the GPU. But if the LLM cannot fit on one GPU, this approach cannot work. To address that issue, there is a zero redundancy optimizer technique. Over there, you split the parameters, the gradients, and the optimizer states in such a way that each GPU trains a part of it. So instead of using one GPU, you use multiple GPUs to train the model in parallel. And with more GPUs, the load on each GPU will decrease, should decrease linearly. And the way it works is you have multiple GPUs, each GPU training a part of the weights, and then we have for each forward and backward pass where you synchronize the gradients, you collect weights, just the weights from all the GPUs, and then you update the model in each iteration. This is the fully sharded data parallel technique. And there is, and yes, in this video you must have noticed we have links to a lot of research papers. So this is the graph taken from one of the research papers where they try to compare or see how the model size has an impact on different training techniques. So this full sharding, hybrid sharding, full replication, and the data parallel. So this T flops is the number of teraflops, or the number of like 1 trillion floating point operations per second. So on small model sizes with 600 million parameters or 2 billion parameters, all these different techniques of data parallel or full sharding don't differ much. But as the number of models, number of parameters increases, for example, to 11 billion, then this DDP just gives out of memory issue. And with sharding, you receive a higher throughput in number of teraflops per GPU. However, if you increase the number of GPUs, there is a slight decrease in the overall throughput, because if you have more GPUs, they will have to, as you see from the previous figure, you will have to exchange or get data from different cores. So this information processing or gathering information from different GPUs has a negative effect on the overall throughput. But still, it's not much. It's like a 7% decrease if you go from 8 GPUs to 512 GPUs. But cumulatively, there will be a higher throughput. It's just like the number of teraflops operations per second per GPU will take a hit as you increase the number of GPUs. Now, to give you an idea of how the floating point operations look equivalent to the GPUs. So if you have 8 NVIDIA V100 GPUs operating at full efficiency for one complete day, then that will be equivalent to 1 peta floating point operations per a day, or 2 NVIDIA A100 GPUs. So you see, compute is costly, and let's continue this in this slide. Now, whenever you work with LLMs, compute is costly, but you want to have a better performance of the model. And you also would like to have as much input training data as possible so that your model is better aware and can predict the output more accurately. So Chinchilla paper has a bit of recommendations around what should be the size of the model based on the number of input tokens it has seen. And this paper says that if we keep the compute budget fixed, then the number of parameters a model should have should be about 20 times the number of input tokens or the number of input words for simplicity. So if, let's say, a model called a GPT-3, which has 175 billion parameters, it should be trained on 3.5 trillion uh, input tokens. In reality, this is trained on just 300 billion tokens. So this is an example of the model which is overtrained. It would have benefited if the number of input tokens were increased. Whereas Chinchilla model and Lalama 65B, which is the 65 billion parameters, for them, the number of actual tokens are very close to the recommended number of tokens. So this is how it works. If the compute is fixed, that is how many GPUs you are going to use and for how long, then your model may be over parameterized because the size of the model is huge and it did not get trained on enough data set, or your model can be undertrained if the model did not have enough parameters or enough weights and the data on which it was trained was huge. So a good balance which the Chinchilla paper recommends is the number of parameters should be 20 times the number of actual tokens should be 20 times the number of parameters on which the model is trained. One more aspect of LLM is even if the language happens to be English, for example, one of the widely used languages, still different domains have different flavors to the language or different dialects to the language. Like the legal and the medical language has got terms and nuances which are little different from the daily usage of the language or the general usage of the language. So if you have such a use case where you would like to have LLMs over domain specific text, then it can be a good idea to pre-train your model over domain specific text. And one example of such model is Bloomberg GPT, which has been trained about half on the general text and about half on the financial text. And Bloomberg GPT follows this Chinchilla recommendation. So the number of parameters it has is close to what the Chinchilla recommends based on their compute budget. And the number of tokens they have, it is also close, but not exactly that close to the Chinchilla recommendation. In fact, it has little lesser number of tokens. And that is because of the lack of availability of enough financial text to train the Bloomberg GPT. Now, let's move towards fine tuning. We have seen some examples of in-context learning. Like if you want to classify a review, you can give some examples and then you can ask your final question. And this is your context window. Now, a few limitations of in-context learning are that smaller LLMs may not gain enough from in-context learning. Even if you give 5-6 inference examples, like a few short inference, still they may not give you good enough results. And the other thing is, the more examples you give, well, these are short examples, but your examples can be long. For example, text summarization examples can be few hundred words or few hundred tokens. So the more examples you give, it will take up the space of your context window, and there exists some constraint on the size of the context window. It cannot be very huge. Usually it's a few thousand tokens. However, recently there have been researches which show that 100,000 tokens, which is close to 75,000 words, can also be passed as a context window. But a lot of existing models as of now do not have that large context window support. So more examples will take up more space in the context window. So in order to deal with those limitations, it's recommended to fine tune an existing model based on your data sets. How this works is, you take an existing pre-trained LLM and you pass some examples specific to your task. A task could be question answer, it could be entity identification, it could be summarization, anything. So based on your task, you provide example prompt and completion, and then you fine tune your model to behave more accurately for these tasks. And that will give you a fine tuned model which will have improved performance on your specific tasks. So instead of giving these examples during in context learning inside the prompt, you can pass these examples in the fine tuning itself. And hopefully, when you uh, ask this fine tuned LLM for this classification, then hopefully you might not have to give any inference examples. You can tune a model based on different tasks. It could be summarization or translation or anything which you care about. In the full fine tuning, all the parameters of the existing LLM are updated. So if the existing LLM has 1 billion parameters, all the parameters will be updated. And the process of fine tuning follows the regular machine learning or deep learning approach, where you have a training data, where you train your model, then you have validation uh, to see how your hyperparameters are performing, and then finally you have test to see the performance of your model. And this is how you split your input training data during fine tuning. So after fine tuning, your pre-trained LLM becomes instruct fine-tuned model. Uh, Instruct fine-tuned model have usually better performance on the tasks they are trained for, but they are equally susceptible to something called as catastrophic forgetting. So you take one model, which is the pre-trained model, and you fine-tune it for a specific task. The problem could be that for that specific task, like classification, the model can become better in doing classification. But for other tasks, other general tasks for which this original model was trained, the model will start to do poorly on that because all the parameters of the models have been updated. As an example, let's say before fine tuning, if you ask the model to classify this, it gives you a poor output. The sentiment should have been positive, negative, neutral. It's not like that. So this LLM was not doing a good job. But after fine tuning, this LLM was doing a very good job, even with a zero shot inference without giving any examples. Now, this is a classification problem. But what if we have some problem of entity identification, like what is the name of the cat? Based on this statement, we have to just predict what's the name of the cat. We have to identify that. Before fine tuning, the LLM had general capabilities. It means it was doing okay on wide varieties of tasks, and it was able to predict that, identify that quite accurately. But after fine tuning, it will say the garden was, it will start to misbehave on those tasks. So in order to optimize for one specific task, the model loses its ability to work on all the other tasks. This phenomenon is the catastrophic forgetting. And why is this happening? Because we are updating all the parameters of the model based on our new requirement, or we are updating the parameters based on our specific task. So in order to avoid catastrophic forgetting, there are a few techniques. But before we go for techniques, the first thing you have to ask is this a problem for you? Do you want to have model just for one purpose? Maybe it is not a problem then. If you don't intend to use your new instruct fine-tuned model for anything else apart from your specific task on which you have fine-tuned it, if you're not going to use it, then it's not a problem. It's fine. You can live with that. But if you intend to use your model on other different tasks, which most likely people do, because LLMs have so many use cases that we would like to make use of them for more than one task. Then there are a couple of techniques. One is the fine tuning on multiple tasks, and other is parameter efficient fine tuning. Let's see them. In multitask instruction fine tuning, instead of training the pre-trained LLM on just one task, we train on examples coming from different tasks. So it could be summarization, classification, translation, identification. We give more examples to the model based on different tasks on which we would like our model to give correct responses. And then we have FLAN, which is the fine-tuned language net. FLAN models are the a specific set of instructions which are used to perform instruction fine tuning. So what happens is FLAN is like the desert. So you take an existing pre-trained model and you create a FLAN version of that, which is instruction fine tuned on your specific task. So for example, you can take a FLAN model and you can fine tune it to generate better summaries. If you are not happy with the summaries they are generating, you can fine tune it so that the generated completion or the generated summary in this case is more close to what is expected. Now, how do you evaluate? Now, for example, let's say you have a pre-trained model and you have fine-tuned it on varieties of tasks. Let's say summarization, for example. How do you make sure, or which metrics do you keep track of if whether your model is moving closer to the expectation or is it moving away from expectation? Well, comparing texts is challenge. For example, if you think about linear regression or logistic regression, if you have to compare numbers, it's much more straightforward. You have a formula and you have to optimize that cost function. But in texts, it could be a bit more challenging. As an example, if you have two sentences like Mike really loves drinking tea, it is equivalent to meaning to the sentence Mike adores sipping tea. Even if these two sentences do not have many words in common, still they are very close in their meaning. Whereas if you have a sentence Mike does not drink coffee versus Mike does drink coffee, these two sentences have a lot of words in common, but they are completely opposite in meaning. So comparing or finding which two sentences are similar or not is more challenging than comparing numbers. And there are a few metrics which can help. Again, these are not foolproof, but still they can help you to just understand how well you are making advancement with each iteration to your model or each iteration to the instruction fine tuning. One score is the Rouge and the other is Blur. Rouge score is used whenever you have tasks like text summarization, and Blur score is when you have tasks like text translation. What happens in Rouge is first you have a reference text, which is the expected text, which is generated from by human during supervised training, and then there is a generated output by the model, which could be something like this: it is very cold outside, and the reference human output is it is cold outside. So Rouge has got different scores, Rouge 1, Rouge 2, and so on. In Rouge 1, what happens is we try to see how many unigrams are matching. Unigrams means one token or one word. So in this case, the reference has got 4 unigrams and the generated output has got 5 unigrams. And we calculate recall, precision, and then based on recall and precision, we calculate the F1 score. Recall is the how many unigrams are matching per reference, and precision is how many unigrams are matching per output. So this reference is the human reference, human generated reference, considered to be the hard truth, and this output is what the model generates. So in this case, because they are off by one word, this is how the Rouge 1 score looks like. Rouge 1 score, I mean, Even if the generated output would have been, it is not cold outside, which is completely different in meaning. They will have the same Rouge 1 score. So that's a downside of Rouge 1. Similarly, for Rouge 2, we take the bigrams, like for example, it is, that will be one bigram, is cold is the second bigram, and cold outside is the third bigram in the human reference. So similarly, Rouge 3 will take 3, Rouge n will take n grams, which is the consecutive uh, tokens or the words. Rouge L score takes the longest common subsequence between the human reference and the generated output. So in this case, the LCS value is 2 because the longest common subsequence is 2 consecutive words, and the other formula remain the same. And the blur score is calculated by taking the precision across a range of n-grams. So if you remember, precision is the number of unigrams. If you take 1 gram, the number of unigrams which match based on the total number of unigrams in the output. So blur is calculated by taking 1 gram, 2 gram, 3 and unigram, bigram, and so across a range of n-grams, we calculate the precision and we take the average. Uh, as a matter of fact, if the output is identical to the human reference, blur score will be 1. And the more close the output is to the human reference, higher will be the blur score. So this Rouge and blur score are fine just because they are cheap to calculate. You can do that when you instruct fine tune a model to see how the model is moving close to the expectation. Is it moving close or is it moving away? But this is not the score which is used as a benchmark. As a matter of fact, we have different benchmarks to evaluate large language models. Glue, Superglue, Helm, MMLU, and Big Bench are some of those benchmarks. These benchmarks evaluate the LLMs across different data sets, across different tasks, and they generate much more useful metrics about the LLMs. But these benchmarks are quite costly to calculate as well. So once you have optimized or fine-tuned your model and now you think it is ready for deployment, you can run it against the benchmark. Glue stands for General Language Understanding Evaluation. Superglue is an iteration of, on top of it. Helm is the holistic evaluation of language models. And then MMLU is the massive multitask language understanding. And they are pretty much in chronological order. Glue came first, then Superglue, followed by other benchmarks. So in Glue and Superglue, they also have leaderboards of different models where they rank different models on their scores. And MMLU and Big Bench, they have wider varieties of tasks and more number of data sets on which to compare LLM, like history, science, physics, child development, mathematics, and a lot more. Helm gives metrics about after evaluating the model, and it gives metrics not only on the accuracy and calibration but also on bias, fairness, and toxicity of the models. So what we have seen is, if the model is prone to catastrophic forgetting, then we can perform fine tuning of the model over a wide varieties of tasks. And the problem is in instruction full fine tuning, all the parameters of the models are updated. And as you know, when we update all the parameters of the models, then it's like a retraining. It's going to be a costly in terms of compute. So there are a few techniques where you do not touch all the parameters of the model, or you do not basically retrain the model. Rather, you retrain some of the parameters in an efficient way, and they are the parameter efficient fine tuning. In parameter efficient fine tuning, again, the idea is to instruct fine tune a pre trained model for your task specific use cases. So one approach in PEFT is uh, we train a small, we update a small number of layers of the actual pre-trained LLM. The other approach is to add a new layer on top of the existing LLMs, and you train only that is the thin new layer which is added on the top. And the whole idea is once you have a pre-trained LLM based on this new layer of weights which you train, you don't update all the weights of the LLM. So all the new the only small part of the weights or a small subset of the weights which you train, you can fine tune your same LLM for different use cases like question answer, summarization, and so on. And all we need to do is we have to find an adapter which can be added to this LLM on like a wrapper on top of it, or like a plug and play adapter, so that the same LLM based on the combination of their adapter can perform different fine tuning tasks. Let's see this in a little bit more detail. Before that, there are different methods of parameter efficient fine tuning: selective, reparameterization, and additive. In the selective, you just choose the initial LLM parameters to fine tune, and the course does not cover this. However, the course does cover LoRa, which is the reparameterization technique, where we use low rank pair of matrices to fine tune an LLM for your task. We are going to look at it quite soon. And then there are additive methods or techniques where you add a new trainable layer on top of your existing LLM. And then one example is using prompt tuning or using soft prompts in prompt tuning. Let's look at both of these. What happens in LoRa is we have a model, and a lot of weights in the LLM are at the self-attention layer in the encoder. Encoder, decoder, both. But let's talk about encoder now. We have weights to the encoder, and the weights of the encoder are kept fixed, and we choose two matrices. The two matrices have low rank, but the dimensions of matrices are such that once they are multiplied, the output matrix has the same dimension as of the weights of the original model. And then we add these two matrices and we perform the iterations and we keep on training it. Remember, while training, the weights of the model do not change. They are frozen. Only these two new matrices, these two new low rank matrices are updated. Uh, as a calculation, let's say if the transformer, the original LLM model, had a transformer weights of dimension 512 by 64, which means it had 32,700 parameters. If we use a low rank of 8 and we train two matrices A and B, which have dimensions 8 by 64 and 512 by 8 respectively, we end up training about 4,600 parameters. So we train it, the reduction in the parameters is 86%. So instead of affecting 32,000, more than 32,000 parameters, we are affecting only 4,600 parameters. And if you multiply the matrix B and A, you will end up with the same dimension of 512 by 64. So the multiplication will match the dimensions of the actual transformer weights. And for different tasks, we can train different pairs of matrices. And this is called the LoRa adapters. Based on what task you are going to work on, you just change the adapter. For example, for task A, this is the yellow adapter. You just change it to green adapter for task B. And this usually is in small gigabytes or even megabytes. If you are just working on your prototypes, your models can be huge, but the LoRa adapters can be way smaller than the size of the models, and you can just plug and play with it. One downside of using LoRa is The performance of LoRa fine-tuned models is usually slightly smaller than that of the full instruction-tuned LLMs, but you get extreme benefit in the size, and you don't spend a lot of compute effort in training your uh, LoRa matrices. There is also an active research on finding what should be the rank of the LoRa matrices. Usually, some rank between 4 to 32 uh, is is a good start number to go ahead. With higher rank, the value loss starts to plateau you. You don't start to get much gain. So a number between 4 to 32 should be good enough to get started with. And further, this LoRa technique can be integrated with quantization as well. So if you want to further reduce the footprint of LoRa matrices, apart from choosing the low rank matrices, you can use quantization as well, so that the size, the model, the memory footprint of the parameters is further reduced. The other technique in the parameter efficient fine tuning is called prompt tuning, or adding soft prompts. So what happens in soft prompts is, as you know, we have the actual prompt, the actual input to the LLM, and these are the words or the tokens. Uh, in this technique, we try to identify, the model tries to identify based on the task what soft prompts should be added at the beginning, so that the model behaves more accurately for that task. Think of it like a hint to the compilers. So while doing programming, sometimes you give some hints the way compiler should work. And based on different hints, the compilers can behave differently. So this soft prompts are analogous to compiler hints, where you give some hint to the model, like based on these soft prompts, the model should behave more towards summarization or towards question answer. So based on different tasks, these soft prompts can be different. And the good thing is this, so these soft prompts are not set by us, rather it is something which is decided or inferred or learned by the model themselves during instruction fine tuning. And because these are learned by the model, and these are the internal embeddings, these are the vector representation, they may not translate into actual words of text. For example, they may not represent any English word or a word of any other language, because but that's not a problem, because these soft prompts are not meant for humans to be understood. Rather, it is meant for the models to perform better and give us more accurate response. So think of it like these are some embeddings which are used internally by the models based on the task. So when doing instruction fine tuning, instead of updating the parameters, we update the soft prompts, and these soft prompts are added in the beginning to each prompt. One thing to note here is prompt tuning and prompt engineering are two different things. Prompt engineering is about how you make your prompt structured, or how you provide more inferences or examples during inference, uh, like zero shot, one shot, n shot inferences. Whereas prompt tuning is something which the model learns by itself, like which soft prompts or the hidden embeddings to add into the prompt when performing completions. And it has been seen that as the number of parameters in the model increases, like it goes to 10 billion or beyond, full fine tuning and multitask fine tuning as well as prompt tuning, they have similar performance, which means multitask fine tuning or prompt tuning start to converge and give similar score. Whereas prompt engineering alone is not that scalable, and it does not match the performance of instruction fine tuning. Now, models let's say you have selected a pre-trained model and you have instruct fine-tuned your model using prompt tuning or any other PEFT techniques or multitask fine-tuning. Still, the output of the models may not always be helpful, uh, honest, or harmless. Models can give toxic, aggressive responses or dangerous information. So the other criteria where we would like to further evolve our model is to align with the human expectations. We want the model to be honest, helpful, as well as harmless. And in order to do so, one of the techniques is to make use of reinforcement learning and integrate that with human feedback. In a reinforcement learning, there is an agent which makes an action based on all the available actions into an environment. And the environment that leads to the change of the state of the environment, and the environment also, and it also receives a reward based on how close it is moving towards its objective. This is an example of the tic-tac-toe game where the agent, which is the reinforcement learning policy or the model, makes an action. The environment over here is the board on which the game is played, and the state of the board is the arrangement of circles and crosses. An action means placing a circle or a cross in one of the empty position, and based on this learning, the objective is to win the game. The agent receives a reward from the reinforcement learning algorithm on depending on whether the action of the agent is making the agent go closer to the objective or not. So based, if the action is taking the agent closer to winning the game, it will receive a higher reward. Now, in case of LLMs, the agent is going to be the LLM, the RL policy is going to be the LLM. And the action it is going to take is to predict or generate the next token from the vocabulary. The environment is going to be the context, or the input, all the tokens which have been generated. And the current context is the state. Here, the objective is to generate the text, the output text, which is aligned to some criteria. The criteria can be honesty or helpfulness or harmlessness. Before we go for an example, let's see how the process looks like. During the process of aligning the model, which have already an instruct fine-tuned LLM, we pass the prompts, the samples to the prompts. And for each prompt sample, we generate multiple completions or the multiple outputs from the model. So let's say if you have 3 prompts, we end up generating 9 completions, 3 completions for each prompt. Then with the human feedback, we have human labeler, which labels the completions based on the criteria. Let's say if the criteria is helpfulness, and for one prompt, there have been 3 completions. All these 3 completions will be ranked like 1, 2, 3 based on how helpful they are. And because a single labeler can be biased or may not always be correct, we can use a set of labelers, and we can take the output of the quorum. For example, we can have 3 labelers, and we can choose, like, let's say if one of the labeler did not understand the instruction well enough, and that labeler ranked the completions in a different order, it will not impact the overall ranking. We can take the majority. For example, for this completion, majority of the labelers have ranked it 1, then this will be ranked as 1. So once we have arranged the completions based on the rank, we use the prompt and the completion to train another model, which is called the reward model. And this is the model which will give a reward, and that reward will be used to further tune or align the instruct fine-tuned model. So this reward model The idea is to take the prompt and completion and generate a reward score based on what alignment you are looking for, helpfulness or harmlessness, and so on. So let's take an example now. So you have a prompt data set called a dog is, and you have to generate the next set of tokens. If the instruct LLM generates the completion as a furry animal, the reward model will give a score based on the alignment. Let's the score is 0.24. And here we are trying to tune for, let's say, harmlessness. Then this reinforcement learning algorithm will update the instruct fine-tuned LLM based on the reward. And this will undergo iterations. So let's say in the first iteration, the reward was 0.24. Now the LLM will be encouraged to generate a score which can get a higher reward. Let's say in the second iteration, this updated LLM generates a friendly animal. Well, this looks more harmless and more polite, then the reward score will be higher. This RL algorithm will again update the LLM to generate a new completion, let's say a human companion. And based on that, after multiple iterations, the idea is this aligned LLM will generate a completion which will give it the maximum reward. Now, after following this process, this LLM, which was earlier just instruct fine-tuned, will be more human aligned in generating the responses or the completions. Responses, output, completions, this can be used interchangeably. A problem with this reinforcement learning as a whole, not only with LLM, but as a whole, is something called as reward hacking. What happens in reward hacking is your updated LLM will try to generate response which may not match the expected output, or it may not match the reality, but it will be generating a response which can give it maximum reward. So in order to go after higher reward, it may end up generating irrelevant outputs, and this phenomenon is called reward hacking. Now, one thing which I skipped was there are a bunch of reinforcement learning algorithms which take the reward and align the LLM to be more close to human expectations. One such algorithm is PPO, which is the proximal policy optimization. The course covers a little bit more details about what this optimization policy looks like. So I would encourage you to go to the course and if you are interested to learn more. But there are other algorithms as well. PPO, however, happens to be more widely used because of its simplicity to understand and use and its effectiveness. Now, as we have seen, reward hacking is where the model will try to generate for better reward, even if the generated output is irrelevant or does not match the reality. In order to do so, we consider not only reward, but we also consider how much the LLM, this RL updated LLM, is diverging from the reality. For to do so, we keep the reference model, which is our original instruct fine-tuned model, and we have this RL updated LLM, which gets updated after each iteration of the reinforcement learning. And we calculate the divergence. One such divergence measure is the KL divergence. This will ensure the probability distribution across the output tokens from the instruct fine-tuned model, which is supposedly more close to the reality, does not diverge much from the probability distribution of the tokens or the words from this updated RL updated LLM. And overall, we take the score from the reward model, and we also take the KL divergence score. So both are included into the RL algorithm, for example, PPO. So the reinforcement learning algorithm considers not only the reward but also how much divergence, how much the updated model is diverging from reality. And based on these two scores, it will update the either the LLM or the adapter. So that's also possible. You need not to adapt, or sorry, you need not to tune all the parameters or all the weights of the reference model. Rather, you can just tune the adapter, which is the parameter efficient fine tuning adapter, which we have already seen before. Now, what we have seen is there was a human feedback loop involved over here, where we have had a lot of human labelers to look at different completions of a model and then rank those completions so that it can be used to train the reward model. Now, having a lot of human labelers, tens of thousands of human labelers, is not scalable. What if this reward model itself can be automatically learned? And that is what happens in reinforcement learning with AI feedback. So instead of human feedback, we use AI feedback. One such example is constitutional AI, where we have a set of constitutions or a set of principles to help a model critique its own response. So let's say there is a model which is very helpful. If you ask how to hack a Wi-Fi, it will give you a response. Well, this is helpful, but this is harmful as well. This is not harmless. So this is not something what we would like to have as an output from our LLM. So in constitutional AI, there are a set of principles which the model must adhere to. For example, choose the response which is helpful, honest, and harmless as well. Keep a track, pay close attention to the response, whether it is illegal or immoral or unethical. So these are some of the principles. There can be more such principles. And then there is a paper on constitutional AI, if you can refer to that for more details. The way this reinforcement learning with AI feedback works is in two phases. In the first phase, we have an LLM, which is instruct fine-tuned model. We provoke the LLM to generate harmful responses. And this process is called red teaming. And then we ask the model to critique its own response as per the constitutional principles, based on the principles which we have already set before. We ask the LLM to revise their response and to comply with the rules. And then we fine tune this LLM using the red teaming prompts and the revised responses. For example, if the helpful LLM gives you something which is helpful but harmful as well, then we ask the LLM, hey, how harmful is your last response? Is it toxic or unethical, and so on? And the LLM can then self-critique and say, hey, the response was harmful because hacking is unethical, it's illegal. Then we can ask the LLM, why don't you rewrite your response and remove all the things which is harmful? And the LLM will rewrite the response. It will generate a new completion based on the constitutional principles. Now, so this was the original prompt, which the red team prompt, which provoked the LLM to generate harmful response. And this is the final constitutional response of coming from the LLM. In phase 2, what we do is, instead of using human feedback, we use this fine-tuned model to generate responses to the red team prompts, which we just saw. And the generated preference data set, the data set which is generated by the fine-tuned model, is used to train another model, which is called the reward model. If you remember, reward model needs the ranked responses, like the ranked completions. And this fine-tuned model now can rank those responses, can help those rank those responses, like based on, if for one prompt, this fine-tuned model generates, let's say, 3 responses, this can rate like this is the best, this is rank 1 in terms of helpfulness, honesty and harmlessness, this is rank 2 and 3 and so on. That data set can then be used to train the reward model. And based on this reward model and the fine-tuned model, we can align our LLM with the preferences. This approach removes the human feedback as we saw before, and hence it is called reinforcement learning from AI feedback. Now, if you remember the generative AI life cycle, first you decide what is your use case, then you decide whether you want to train your own model or use any pre-existing model. You can fine tune it, like instruction fine tune. You can use PEFT. You have aligned your model with human feedback. Now it's time to deploy the model. When you go for to deploy the model, there are a few optimizations which you can do at the time of deployment. Deploying the full model may be not cost effective. So there are three techniques to take use of. One is distillation, quantization, and then the last one is pruning. What happens in distillation is using a bigger model, we train a smaller model. The smaller model is called the student model, and the bigger model is called the teacher model. Uh, with the student model has got we try to optimize for two losses. One loss is the student loss, where we compare the probability distribution across tokens of the student model with respect to the ground truth or the training data or the human generated output. And we also compare the output of this LLM, student LLM, with the output of the teacher model. Essentially, when we say output, it's the probability distribution across different tokens. One thing to note is there is when comparing the output of the student model with the ground truth, we try to go for a temperature setting of 1, which means the LLM student model should match as close as possible to the ground truth. But when comparing its output to the teacher model, we give LLM a little bit more creativity, and that is called the soft predictions, which set the temperature more than 1, so that we LLM model can diverge a little bit from the output of the teacher model, and it can be hence be a bit more creative. So in a way, this LLM student model is still aligned to the ground truth, and it still learns from the teacher model, but it has some degree of freedom in terms of how much it can diverge from the teacher model. Well, the whole idea is LLM student model will be a smaller model, and this is what you can deploy and external applications can then talk to. We talked about quantization during training. This quantization can be used during deployment as well, which will reduce the precision of the weights. Instead of using 32 bits for float, we can use 16 bits of brain float numbers. And the other technique is pruning, where we remove all the weights of the models which have values close to 0 or equal to 0. This, however, is not widely used because only a small number of weights in the LLMs are 0. But it can have benefits if there are lots of weights, lots of 0 or close to 0 weights, then you just to reduce the size, you end up reducing the size of the final LLM which goes to deployment. Now, even if a model is deployed, the LLM is prone to a few other issues or challenges. One problem is the model can get out of date. So let's say you trained your LLM on lots of text data, and at that time, the Prime Minister of UK was Boris Johnson. But if you query the LLM currently, the Prime Minister of UK is no longer Boris Johnson. So the data on which the LLM was trained can get out of date, especially if the data is more related to the current affairs. The other problem of LLM is they are not meant for doing mathematical computations. LLMs are suited to predict the next token based on the tokens it has seen so far or it has generated so far, and also based on the input prompts. So if you expect the LLM to do mathematical computations, it's likely that the answer will be wrong. The other problem is hallucination, where the model will give you incorrect result, and the model thinks it's a correct response, but in reality, it's not correct. So in order to overcome these shortcomings of LLMs, first of all, to deal with out of date data, you may wonder why not we uh, train the LLM quite often. Well, training the LLM is very expensive affair. You cannot do that every day, especially if it's a big model. And so keeping it in sync with the current reality is something which cannot be fixed by multiple retrainings or frequent retrainings. And for the other challenges as well, retraining is not going to help. So in order to overcome these shortcomings of LLMs, we can use an orchestration library which can interact with the LLM, and it can interact with other external data sources or other external applications or interfaces. Let's see some examples to get more understanding. One such technique is the retrieval augmented generation, or RAG in short. So what happens in RAG is we have query encoder and external information sources. This external information sources may be a vector store which contains the embeddings of the text, or it can be any text store as well. You receive prompt in the query encoder, and this query encoder and this external information sources are trained in such a way that based on the prompt, it we can find a relevant document from the external sources. One good thing about external information sources is it need not to be publicly available. It can be something private or proprietary to your organization, where you can have full control on what to search, how to search, and what confidentiality level has to be maintained. Well, the whole idea is you receive a prompt or an input via query encoder, you find a matching or a relevant document from the external sources, and whatever text you get from the external sources plus the prompt are added or concatenated together to the LLM, so that LLM can perform its operation like identification, summarization, whatever the task is. The idea here is this content of the external information sources is now decoupled from the LLM. So LLM need not to keep track of this, or need not to get retrained every time this external information sources is updated or added. For an example, let's say the query encoder receives a query like, who is the plaintiff of this case? A search will be made into the external document or external information store, and let's say this is the matching, the text which most closely resembles to the input query. Now this text, which has been fetched from the external information store, is then passed along with the query to the LLM. Now the LLM has got the access to the latest up-to-date information along with the question which was asked in the original prompt. Based on this, now this is the whole prompt which will be passed to the LLM. LLM can now easily perform its task which it is best at. In this case, it's the case of question answer, or it's a case of entity identification. It will generate a completion. The good thing is the information over which the question is based on is now not a responsibility of the LLM anymore. The other challenge of LLM is it can struggle with complex reasoning problems. For example, if you have a question like someone has 5 tennis balls and the person buys 2 more cans of tennis balls, each can has 3 tennis balls, how many tennis balls does the person has now? This is not a text generation in a way, rather this is a problem of reasoning. You have to go step by step. If you do this input to the model, most likely you will get a incorrect response. To go around such statement, if you think like a human, you have to go step by step. First, what was the balls to start with? Second, how many cans of how many balls each were purchased? And so how much new tennis balls are there? So these are the new balls, and then there was some balls before, you added up, and the answer is 11. So these steps are the reasoning steps, and these form the start steps and end form a chain of thoughts. This is usually how a human will go around thinking about it. We can use this approach to enable our LLM to think in chain of thoughts approach. So one way is we can give this as one shot inference, like this is the question. So in order to solve questions like this, these are the steps you have to follow. And then you ask the final question. So you give one example and you ask one question to the LLM. Hopefully LLM will give you a better response this time, because now LLM is a bit more aware. This is an example of in context learning where you are giving you are making one shot inference. However, you can instruct fine tune your LLM for such use cases also, for such chain of thought prompting. Now we saw that LLMs are also prone to give you incorrect response if it involves mathematics. So why not offload the mathematical computation part to a system which is better suited to do that? For example, why not do this mathematics inside a Python interpreter? Because Python interpreter can do accurate mathematics than LLM. And this is the idea behind the program aided language models. The idea of program aided language models is to generate a Python code which can run inside a Python interpreter. As an example, the same question can be deconstructed into these steps. Like we can generate a Python code, something like this. You see all the comments are starting with hash, and these are the reasoning steps. Like in the chain of thought, what is the reasoning? How many balls they start with, and so on. Now, if you run this Python code against Python interpreter, you will get an accurate response. So if you provide this as one short example, you provide one example of such situation, and then you ask a new question, hopefully LLM should be able to give you a generated Python text along with the comments which explain the steps, the reasoning involved, and this whole code can be then run against the Python interpreter to get a response. And that is what the duty of orchestration library is. In program aided language architecture, based on the input from the user, LLM can generate an executable code which the orchestration library will run against the Python interpreter to get a response. So basically, we are complementing the features of LLM with some external interfaces, which happen to be Python interpreter in this case. So in order to overcome the challenges with LLM, this orchestration library can be very helpful. One more thing which is covered in the course is about React, which again enables to do complex chain of thought reasoning along with action. So React has 3 steps. One is the question, four steps. Based on the question, it starts with a thought, performs action, and makes some observation. For example, if your question is, which magazine was first started, Arthur's Magazine or First for Women? Now, what will be the thought? The thought will be the reasoning step which will identify how the model is going to go around tackling the problem, and it will also identify the action. Very similar to how a human would do that. So if you have to answer this question, first you need to search Arthur's Magazine and First for Women and find out which one was started first. So that's your thought. How would the action look? Well, action also depends on what external APIs you have at your disposal. In this research paper, there were three APIs. One was search, lookup, and finish. Search was to find a Wikipedia page for the entity. Lookup means once you have found a Wikipedia page, you try to search for a string in that page and get a paragraph or two from that Wikipedia page. And then you complete your action with a final with an answer, which is finish. So in this case, first we search for Arthur's magazine. Let's say you found a Wikipedia page, then you search for the string. And let's say this is the paragraph you found on the Wikipedia page, like Arthur's magazine. This is the period was American literary periodical published, and so on. Now, next, you repeat the loop, you run it in a loop, you repeat the process, and your you search for first for women, and your observation is that first for women is a women's magazine published by someone, and it was started in 1989. Now once you have these two observations, your thought will be first for women was started in 1989. Arthur's magazine was started in 1844, and then you can compare which came first, and that will be your final action. Like, okay, Arthur's magazine here came first, it was published first. So basically, trying to sequence your steps in terms of thought, action, and observation, this is how React tries to achieve. It tries to amalgamate the reasoning along with action. So you can pass this React example along. So you can pass the instructions along with the React example, and then the question which you want to be answered as the whole prompt to the LLM. And hopefully the LLM will try to follow your hint or try to follow your example to generate the response for the question which actually you want to get answered. Now, LLMs may also be required to produce outputs which are formatted so that the external applications or the orchestrator can better understand them. For example, format the output to run a SQL query to understand whether there exists any order ID as a such or not. Similarly, in order to validate certain actions, you prompt the user to provide their email ID and make sure that the email ID exists. So input as well as output, both from the LLMs at times need to be structured so that it can very well play with the orchestrator or the external applications. And one such orchestrator tool is LangChain. LangChain gives you tools, prompt templates, memory, and agents. These prompt templates are the structure to structure the input or the output. Memory is to store the interactions with the LLM, and these tools are to carry out different tasks like talking to external data sets, making API calls. And then agents are the one which interpret the input from the user, and then they determine which tool or tools to use for the task. So with LangChain, you can talk to external data sources and APIs as well. You can talk to LLMs, and this is your orchestration library where the user application can talk to. Finally, let's move towards the end. In order to build the generative applications, your LLM models are a one part of the bigger picture. Ultimately, you have to host your LLM models or run your models on some infrastructure, which will be your compute, which network, storage, memory, and so on, where you will be training and fine tuning as well as serving your model. You need to store the generated outputs and feedback on how you can further improve your model and so on. You need external or internal data sources where your orchestration library is going to connect to. On top of it, if you go higher the stack, you need LLM tools and frameworks like Model Hubs, which gives you a lot of existing models, or LangChain, which happens to be the orchestration library. And then finally, there will be a website or some kind of application interface where the users or the consumers are going to connect to. It can be website, it could be APIs, it could be mobile applications. So you see, in the whole in the bigger scheme of things, LLM models are quite important, but you will have to think about the other parts of the whole end-to-end deployment and usage of that model. When it comes to responsible AI or responsible generative AI, there are some of the important challenges of toxicity, hallucinations, and intellectual property. In toxicity, LLM returns responses which can be discriminatory or harmful. In order to protect that, we need to have a careful curation of the training data, which will require human effort. But we can also guard, we can we can train the guardrail models so as to filter out unwanted content. Constitutional AI is one such example. And the better the diverse human annotators are, the better it is, so that you are not biased, because what can be sensitive to one uh, may not be sensitive to other. So it's good to have a diverse group of human annotators. Hallucinations is where LLM generates incorrect information, thinking that thinking itself that it is correct. In order to combat or minimize that, first of all, we need to educate users about how generative AI works. It may not be always 100%. It's your helper, but it's not something you can trust every time. Better to add disclaimers. You, as we saw in RAG, we can augment the LLMs with external databases or independent verified citation databases. We can also explain what is the intended use case and what is not. For example, if your LLM is meant for text summarization and you are using it for question answer, then it's good to add disclaimer that that's not the main purpose of using this LLM. It's also quite risky that if LLM discloses the intellectual property or the internal information about any organization, at the same time, it's equally risky that we need to risky that people can plagiarize the content or copy the content. In order to mitigate that, there has to be a bigger governance where a mix of technology, policy, and legal mechanisms have to play hand in hand to ensure this is governed. Machine unlearning is one approach where the machine tries to unlearn some of the things which are quite sensitive and which should not be exposed. So you have to assess the risk for each of the use case you identify and then evaluate the performance of the model in an iterative way. Some of the ongoing researches of AI include how to have a responsible AI. This is something a lot of people are working very hard to ensure it. How to predict the performance and they scale the models. Also, how to increase how to increase the capabilities of LLM, especially the multimodal capabilities, where you try to augment the text generation capability with computer vision or with audio and so on. So that was it. Thank you for watching this video, and this was the summary of the course. As I said before, all these slides have been taken from the course. They belong to deeplearning.ai. This is the course. In case you see, as of today, there are more than 125,000 students already enrolled. So it's a very popular course which has got a very high rating as well. And however, it says intermediate level, but I think even if you are a beginner, you will be able to understand a lot of things mentioned in the course. And it's not a big course, it's just a 3 weeks course. Well, I'm not promoting the course, but it's something I must mention because this content is the summary of it. There are a lot of research papers, more than 2 dozens of research papers have been linked. If you are interested to know details of anything, the research paper is the place to go for. Also, try to get some hands-on in order to get a better flavor of how actually working with data, the data looks like. This video was mostly theoretical, kind of high level skimming through all the different contents and topics you can expect from the course. But once you do the hands-on, it will help you develop more confidence. With that said, thank you so much for your attention.